go solve an inequality that involves a quadratic. Bigger than, less than, bigger than or equal to, whatever. Let's replace that 0 with a K. So first find the places where equality happens. Those are the endpoints of the solution. And that now gives you like a number line. It's a quadratic, so you know you'll have two solutions, or maybe one. That's possible. After that, I only see 3 intervals made out of those. You just need to decide whether each of those intervals is included. You can do so by thinking about the graph. You can do so by thinking about plugging in some sample points. And then be careful with the endpoints. Does that feel pretty okay? And you know what, I think there are let's do like 3 things from here before I move on. It'll be okay. The first thing I want to do is one where something weird is going to happen. There's a quadratic function. Let's figure out the one at the very bottom. Let's figure out where that is strictly bigger than 0. And so we have a plan. Step 1, figure out where it's equal to 0. Then check some sample points around those endpoints. And let's see. Gesundheit. How do people feel like they want me to be the one to solve that quadratic equality? Cool, then I will. So let's solve that. So step 1, solve x squared minus 2x plus 1 equals 0. And on the one hand, you might notice that that factors, but let's imagine that I don't. If you want to use the quadratic formula, what do you get? You'll get x equal to negative b, so 2 plus or minus the square root of b squared, so 2 squared is 4, minus 4 times a times c, all over 2a. And now it's just a matter of evaluating that thing. And I guess the place to start is inside the square root. You walk out the number inside that square root, what do you get? 0? What's the square root of 0? 0? Does it matter if you add or subtract 0? Oh, cool. So like that bit all goes away. That's just 2 over 2, also known as 1. Ah, so there is exactly one solution to this quadratic equation. And now, let's solve the inequality. So let's see, let's do it both ways. So on the one hand, there's 1. That's the place where equality happens. The 2 strategies we kind of explored last time is we like check some sample points away from 1. Or we look at a graph. Yeah.
Would that be 1 and negative 1?
1 and negative 1. Why negative 1?
This isn't it 2 plus or minus? Oh wait.
It's 2 plus or minus 0.
Yeah.
Adding 0 is the same as subtracting 0. Yeah, the plus or minus is in front of the negative b terms, in front of the square root. So let's pick some sample points. Give me something less than 0 I could plug in. Less than 1 I could plug in. 0 walk, negative 1 walk. I think 0 is the easiest. So let's test x equals 0. When you plug in x equals 0 to that formula, what do you get? I think 1. Nice. I want to solve phi of x strictly bigger than 0. Does that satisfy the inequality? All right. So that looks like everything to the left of 1 should be included. And you might be tempted to say, well, that means that everything to the right of 1 is probably excluded. It should probably change. But, you know, to be intellectually honest, you have to check. So give me a number that's bigger than 1 to check. 2. What do you get when you plug 2 into that formula? Also 1? Oh wait, that's also bigger than 0. Everything bigger than 1 is included. So everything bigger than 1 is included, everything less than 1 is included. The only thing that leaves to check is 1. Is 1 included? No, why not? Yeah, I want to know when this thing is strictly bigger than 0. X equals 1 corresponds to phi equals 0. All right, so that picture tells me the answer. Negative infinity to 1, together with 1 to infinity. Or if you wanted to write it in ones, all real numbers but 1 will work for me. That feel okay? Nice. So that's a weird thing that can happen when there's only one solution to equality. The algorithm still works, but it can give an answer that might be surprising. Let's also see this graphically. So, what do we see here if we were to graph this thing? Well, we'd see there's only one x-intercept at x equals 1. It's a parabola, upward opening or downward? Upward. Oh, cool, so that also has to be the vortex point, doesn't it? Otherwise, if it went down through the x-axis, it'd have to come back up. So, graph looks something like this, and now you can read out the answer. Well, it looks like all these y values, yeah, those correspond to output values bigger than 0. Everything to the right of 0 also results in output values bigger than 0. You get the same answer. That feel pretty good? All right. So, sometimes you can get weird situations when the solution to the quadratic equation is weird. When it has no solutions, you still have to do some work to figure out what the solution set is. When there's only one solution, same. Since maybe on things like exams, I'll ask multiple choice questions about solving quadratic inequalities. Let's see how much we can take advantage of a multiple choice problem in which I ask you to solve a quadratic inequality. So there's one. Let's find the solution to x squared plus 2x minus 4 strictly bigger than 0, given that it is one of those options. So let's see what we can do automatically. So don't try to actually directly solve it. I want to take advantage of the fact that this is a multiple choice. What options can you discard without even thinking? Are there any? Yeah.
A and B.
Why A and B? What did you do to exclude those? I'm not saying you are, I just want to know why.
Because it only has one value. I think there are two different values.
Both of those are intervals. They're like the plus versus the minus changes it. Right, like negative root 5 is like negative 2-ish. So that's like negative 3-ish to 1-ish. Well, how about this? So I'm not, yeah.
You can get rid of B and D
B and D. Why B and D?
because you're not including anything.
Nice. Whenever you want to solve a strict inequality, the endpoints correspond to equality, don't they? So we better not be including endpoints because we know that we should be excluding them. So that leaves us A and C to decide between. How could we decide between those? Ideally without having to actually compute anything, but. What's the shape of the graph of that thing, of the quadratic function in this question? Parabola? Upward opening or downward?
Upward.
Let's draw that picture. Because this says that the solution should be a space in between two numbers. That one says the answer should be the space beyond. So let's see what the graph says. And I don't even need to worry about the graph being correct. It's an upward opening parabola. I want to know when the y value is bigger than 0. Do I want something that looks like negative infinity to a number and a number to infinity, or something between two numbers? The one with infinities, I think. That value, oh, that corresponds to bigger than 0. So I need all of these to be included. These will be excluded. Those should be included. Cool, so what's the answer?
C.
Nice. And we could have done that like directly by actually finding the answer and then seeing which one it was on the list. But remember, you can take advantage of the fact that multiple choice problems are designed the way they are. Yeah.
What we just did, just drawing the graph, would that be considered like good enough work if this was like a quiz?
Oh, cool. So if you have a multiple choice problem on a quiz, if you have the right answer, I won't read the walk at all. You'll get the points. But if you do all this walk and you say, well, I'm kind of novice, here's what you do. This thing looks like phi of x bigger than 0. So exclude end points. Decide between A and C by graphing. Right, like, give me a story about your strategy. And then even if you like screw up a detail of your strategy, at least I know your strategy. And like, I don't expect a lot of walk on multiple choice problems. It's enough that I have something to grade, even if you have the wrong answer. And like, if you do show all the walk and I notice you like add 2 and 2 and get 5 and get the wrong answer because of that, as long as I can detect that fact, you'll get most of the points. Yeah.
I was gonna ask, what is like most points you can get if you get it wrong in your work? Like half?
Usually the multiple choice are out of 5 points, and if like you just screw up a bit of arithmetic, you'll get 4 out of 5. If you screw up something more major than that, then you get 2 or 3 of the points. If like I can detect something that might be an intelligent thought, but I'm not sure, maybe you'll get 1. So I mean, I use the whole grading spectrum. Nice. People feel pretty good? Last thing I want to do is let's combine this idea of inequalities with domain. I don't want to jump down to the example of the follows, but in fact I've changed the function. Let's find the domain of a square root. And let's make it the square root of x squared minus 2x minus 8. And whenever you want to find the domain of something, think about what the domain means. The domain is like all of the inputs which result in outputs that make sense. And so, what could possibly go wrong with this function? What could make it not make sense? Yeah.
It has negatives.
A negative being under the square root. So the thing under the square root can't be negative, so it's either positive or 0. So to find the domain of this thing, so that means x squared minus 2x minus 8. The thing under the square root has to be bigger than or equal to 0. Is there anything else that could possibly go wrong there? Is there any division that could result in division by 0? No. There are no other square roots. Eventually we'll talk about logs, and those have other domain restrictions, but there are no logs in here. So yeah, we just need to solve that inequality. That inequality look not unreasonable to solve? Yeah. Well, I guess like the same question. Should I do it or should I be quiet? Should I do? Cool. Then you got people around you to walk with. Go through the steps to solve that inequality. If you want to do things related to a class other than this class, you can just don't do it in this class. So, like if you just have a big test that you need to prep for and you'd rather do that, then like you can just use your stuff. Otherwise, like that looks like not my class stuff to do. Yeah. So put it away or get out of here. Sorry, that was rude. And like those, yeah. As you're making progress, even just as you like find the roots of the equality, you can compare with those around you. Gesundheit. All right. Let's hear it. So, I guess first things first, step one was, well, I mean, how about, what's the answer? What's the domain of this function?
4 to infinity.
Say that right?
4 to infinity.
I hear the interval from 4 to infinity. Include or exclude that 4?
Include.
Do I hear agreement or disagreement? Do I hear an agreement? Do I hear a disagreement?
What do we do with the -2? Because I got -2 as well.
Nice. So, I think -2 is relevant. So, why doesn't your answer have a -2 involved?
Because of the square root.
Ooh, x can be negative. The thing under the square root can't be negative. So I think, in fact, the domain's more like that. And let's talk about why. And maybe before we even talk about why, let's just do the quick sanity check. So like, you get that interval and you think, well, gosh, I don't want to have a negative under a square root. Let's actually just test an input in -2 to infinity and see what happens. Give me an input in between negative infinity and -2.
-3.
-3. So let's test x equals -3. Let's see what happens when we plug that into this function. We'll get the square root of -3, but then it gets squared, minus 2 times -3, minus 8. And we just have to work out what it is. So 3 squared is 9. Minus 2 times minus 3 is the same as plus 6. Minus 8. So let's see, I worked that out. I think that's root 7. Is that a thing that exists? Oh, yeah. So that means -3 is in the domain. So, a thing to remember with square roots is when you see a square root, the thing under the square root can't be negative. It doesn't say that, like, nothing can be negative. Just the exact thing that you see under the square root. Cool. People feel pretty good? Nice. Good, then I'm glad I asked that, because this is like, that's like an obvious stumbling block that otherwise I'm sure can't get. Just because you see a square root doesn't mean x can't be negative. It just means the thing that you know can't be negative. Yeah.
Is there a way to I'm sure we did this, I was just struggling with it. Is there a way to like solve by doing the square without using the quadratic formula?
Oh, sure. I think, well, we found integer solutions. So I know that that thing's going to factor. So right, if you want to solve the inequality, right, you want to do x squared minus 2x minus 8 equals 0. There's like step 1. Or is that what you mean? Like, you can factor this. And I know you can because I get integer roots.
Yeah.
How many people actually just factored it? Cool. It's a little easier.
I've been struggling how to figure that out.
Oh yeah, then let's talk about how. So it's going to factor as x plus or minus something times x plus or minus something. I need these two things to multiply together to be negative 8. So two things multiplied together to be a negative, one has to be positive, one has to be negative. Doesn't matter which one I put where. So now I need two numbers that multiply together to be negative 8 and add together to be negative 2.
So negative 4 and 2.
Negative 4 times 2 is in fact negative 8. Negative 4 plus 2 is negative 2. Yeah, that checks out. And in general, when you're trying to factor a polynomial like this, like you can be guided like that, but when in doubt, you can just check all the damn factors of 8.
And this doesn't always work.
It does not always work. Whenever you get to the end and you see that there are a whole number of solutions to equality, then you know it would have worked, but it's kind of too late to take advantage of it because you've already solved. But yeah, you do that, negative 1, 2, so x minus 4, x plus 2. Now you need to set that equal to 0. And now it's easy to. That one gave you the negative 2.
So I need to solve for x.
Awesome.
Thank you.
Yeah. And maybe as a reminder, factoring is useful when the other side of the equal sign is 0. X plus 4 times x plus 2 equals 7 isn't so helpful because there are lots of ways to multiply things together to get 7. You don't know that one of the two has to be 7. All right. People feeling good about quadratic inequality? Nice. So, we're coming up on the end of this pack of notes. Last thing I want to hit is a few things about complex numbers. So like, we've seen a few situations where we've been talking about stuff under the square root, and we've got like negatives under there, and we've just, as soon as we see a negative under a square root, we say there are no real solutions. And that's absolutely the right thing to do. Like if you're trying to solve an inequality, you're trying to optimize, like you want a real input that produces the optimal output. But sometimes it's useful to produce solutions that aren't real. It's things that are like extended numbers. And in order to see like the idea behind why complex numbers are reasonable just historically, like you've done exactly the construction of complex numbers at some point in the past. In fact, if I say complex numbers, how many people have seen them at some point in their life? Cool, not everyone. That's good. Let's talk about what the idea is behind complex numbers. So I get myself in situations where there are some equations that I'd like to solve that just don't have solutions. Like x squared plus 1, that has no real solutions. No square is going to be negative 1. But like I still want to talk about a solution to that thing. And like that fits into a historic pattern. So maybe you only believe in counting numbers, right? Like I can't have 2 thirds of a sheep. 0 sheep doesn't even really make sense. I just don't have any sheep then. You can't solve all equations if you're in that situation. If you only believe in those numbers, then does x plus 2 equals 2 have a solution? No, but like it does have a solution. What's the solution to that equation? 0. 0. So you need to believe in 0 if you want to solve that equation. So instead of thinking about natural numbers, you have to think about integers. And integers are things like positive or negative natural numbers, together with 0. But even then, 2x equals 1, does that have a solution if you only believe in whole numbers? No, 2x would be even. 1 is odd. So it doesn't have solutions if you only believe in integers. But it does have a solution. What's the solution to 2x equals 1? Right? So you need to believe in fractions if you want to solve equations that involve multiplication. All right. Well, let's say you're allowed to look at natural numbers. Well, what about then? Does x squared equals 2 have a solution if you're only allowed to look at rationals? No, right? Because what's the solution to x squared equals 2? Square root 2. Or negative square root 2, I guess. But that's irrational. Sales pitch. The extra credit at the end of this section is going to have you show that the square root of 2 is in fact not a rational number. And it's like a really classical argument, but it's one that's worth seeing and going through. But like, square root of 2 is still a number. Like, you can get a decimal expansion for it. It's a real number. So like, as equations get more complicated that you'd still like to talk about solutions to, you need more numbers. And so here's this last one. X squared equals negative 1. Does that have a solution if you only believe in real numbers? Nope. A square will be positive. Or 0. So instead, what is that number? The solution to this is a complex number. It's a number that I have to make up. And then we'll study the properties of. So, complex numbers. So let's write down a definition. And I don't know, a bunch of you have seen complex numbers before. Like, what is a complex number? What's an example of a complex number? Yeah, like there's this doodad that we'll call I. Although, is anyone in this room like electrical engineering adjacent? Oh, okay. Electrical engineers like to use J because I means inductance for their complex unit. We won't in this class, but if you're an electrical engineer, you might.
My father is, and I was wondering, do you talk about J different types of numbers? What does that mean?
Yeah, it means I.
No.
So, overview of complex numbers. We want to be able to solve x squared equals minus 1. So I'm just going to conjure up out of nowhere a solution to that equation and I'll give it a name. The complex numbers you get if you just conjure up a new imaginary unit I, or j, with the property that its square is negative 1. This thing is also called the square root of negative 1, and I'll sometimes write I equals square root negative 1. So I'm just inventing a new concept that I'm calling a number. It's not a real number, it's something else. So I'm calling it imaginary, called I. But if I add together two numbers, I should still get a number, right? So if I is a number, like 7 times I should be a number. 3 plus 7I should be a number. In general, anything that can be written as A plus BI with A and B real is a complex number. So a complex number is any number that can be written as A plus BI with A and B real. Feel pretty okay? All right. So if that part B is 0, then A plus BI is just a real number. If A equals 0, then A plus BI is BI. I will call that an imaginary number. So every real number is a complex number, it just has 0 imaginary part. An imaginary number is a complex number that has no real part. So not every complex number is imaginary, but every imaginary number is complex. Every real number is complex too. All right, feeling good right now? Nice. So we have these doodads called complex numbers. What sort of things are you supposed to be able to do with numbers?
Solve them.
Say that louder?
Solve them.
Oh sure, I should be able to like solve equations. But let's look like lower picture, like lower scale than that. I should be able to like add them. I should be able to subtract them, multiply, and divide them. So let's just explain how you even define what addition, subtraction, multiplication, and division mean for complexes. Addition and subtraction are like obvious. If I just give you two complex numbers, 2 plus 3i minus 1 plus 4i, what would you want that subtraction to be? Well, let's go through it. I should be able to like distribute that minus sign, right? Like that just should walk. So that should be the same as 2 plus 3i minus 1 minus 4i. And now this is like gather the common terms together. What's 2 minus 1?
1.
If I have 3 i's and I take away 4 i's, how many i's am I left with?
1.
1, but it's negative. So, whenever you want to add or subtract complex numbers, just do the most obvious thing. A plus bi plus c plus di is a plus c plus b plus d I. A plus ci minus c plus di is a minus c plus b minus d I. If you want to multiply complex numbers, yeah.
1. The answer is 1.
The answer to what?
Multiplying. So I squared should be 1.
Negative 1.
Oh, yeah, that's right.
It's not exciting to invent a new number whose square is 1. You already know a number whose square is 1. You want to invent a new number whose square lets you solve new equations. I squared is negative 1. So if you want to multiply, you just need to use that and like this concept of foiling. So I think instead of doing it in abstract, let's do it in a particular. So if I asked you to multiply that together and I said the word foil, let's just go through and do it. So it will be first times first is 8, outside minus 8i, inside plus 6i, last. 3 negative 2 is negative 6, I times I is I squared. That feel okay right now? All right. So there's most of the walk. Now let's just use I squared equals negative 1 and combine like terms. So let's focus on this negative 6i squared. What's I squared? Negative 1. So that's negative 6 times negative 1. What's negative 6 times negative 1?
6.
Plus 6. All right. So all of this, that's minus 6i squared, is plus 6. So this is 8. May as well combine these two terms together. Minus 8i plus 6i is negative 2i plus 6. Any more simplifying to be done now? Yeah, what do you see?
You take 8 plus 6.
Yeah, 8 plus 6 is 14? Yeah. Groovy. So in general, if you want to multiply two complex numbers together, maybe I won't even write down the formula because the formula is not like that useful. Foil and use I squared equals negative 1. Yeah.
So if you have like 3i cubed, you can't simplify that?
Ooh, yeah, you can.
You can?
Let's do it. So let's think about what 3i cubed means. Like that?
Yeah.
So that would be 3i cubed is I times I times I. So now that we've written it out that way, do you see anything, does anyone see something useful we could use there? What if I focus on just like these two terms together? that's I squared, right?
Yeah.
So this is the same thing as 3 times I. So there's still an I times negative 1 minus 3I. So it does simplify. In fact, if you have any power of I, you can always reduce it to just a power of 0 or a power of 1 on the I.
So if it's odd, it's always going to be just I.
There will be an I at the end if it's odd, but maybe an extra negative sign will get kicked out.
Okay.
And if you like, the way to decide is think about something a little bit more than just even or odd. Think about like what the remainder is after you divide by 2, after you divide by 4. So right, if it's a multiple of 4, then it would be I times I times I times I. 2 of the i's grouped together to be a negative 1. 2 of the i's grouped together to be a negative 1. Negative 1 times negative 1 is 1, so it all cancels out. So I to the 4th is 1. So you can use that to help.
Okay.
Cool. Nice. That helpful? All right. So let's see something a lot like that. Let's use this idea of foiling and that to compute something a little bit more sophisticated than just a product of two things. Let's compute a product that's 4 times long. Let's compute 1 plus I to the 4th. So that'll be 1 plus I, 1 plus I, 1 plus I, 1 plus I, and that, I think, is 4 of them. Didn't lose count. So if you wanted to compute that product, like, what ideas do you see? Yeah.
I see 2 different I squares.
Yeah, I think I will in a moment, but I think first let's just directly FOIL out each of those 2 things.
Okay.
So let's do it. 1 plus I times 1 plus I. I don't know, should I do the multiplication of 1 plus I times 1 plus I, or should you? Should I? Cool. Then take each of those terms that I have underlined in orange, walk out what that product is, and tell me what you get. Maybe even compare with those around you. Cool. People feeling confident? What do we get? No, just the one thing I underlined in orange. 2. Nice. So the thing underlined in orange is 2I. This is the same thing, so it's 2I again. Does that agree with what people got? Nice. So what is that? I hear a negative 4. Oh, cool. That's kind of neat. In fact, if I were to ask you, what is a solution to x to the 4th equals negative 4, could you now tell me a solution to x to the 4th equals negative 4? Yeah, 1 plus I. I mean, you didn't find it, you like happened onto it by like checking a thing. So like, I'm not going to tell you how you produce that. Has a solution is x equals 1 plus I. And in fact, here's a cool fact about complex numbers. If you write down absolutely any polynomial equation, it has solutions, as long as you're willing to look in the complex numbers. Every polynomial does. All right, so we can add, subtract, and multiply, and that's all pretty straightforward. We should be able to divide numbers by each other. And this is the only one that requires like some amount of sneakiness. And here's like the motivation for how to divide. If I asked you to do 2 plus 3i and then divide that just by 7, what would you want to do? Divide each term by 7, right? Division should distribute over addition. So if I'm going to try to do something like 1 plus I divided by 3 minus 2I, that's too complicated though. I don't know how to divide by a complex number yet. But if I can figure out how to turn that complex number into a real number, then that will be a good starting point. So what's a way to turn complex numbers into real numbers? Well, just kind of like if you want to see a square root of 2 in the denominator, you'd multiply and divide by a square root of 2 to turn the denominator into a rational. We'll do the same thing here. We want to multiply and divide this by something to turn the denominator into a real number. And how will we find that real number? We'll do something called the conjugate. And so now up here, what is the complex conjugate? It's nothing complicated. It's just the thing you get by taking the imaginary bit and putting a negative sign in front of it. A plus IB complex conjugate is A minus IB. And why is this useful? This is useful because of the example that we're about to walk at. So, 4 plus 3i times 4 plus 3i complex conjugate. Let's walk out what that is. So doing that, let's see, that'll be 4 plus 3i multiplied by 4 minus 3i, because that's what the complex conjugate does. And now, I guess we have to FOIL it out. 4 times 4 is 16. 4 times 3 is 12. There's a negative sign and an I. Minus 12i. 3 times 4 is 12, plus 12i. 3 times 3 is 9. There's a negative sign, so negative 9i squared. So that got more complicated before it simplifies, but what simplification do you see that you can take advantage of now? Yeah.
Negative 9 I squared.
Cool. What is this the same as?
9.
Plus 9? The I squared is negative 1. That'll cancel with that negative sign. Any other simplification you see?
Negative 12I and 12I plus 9.
Yes. All right. So this works out to be 16 plus 9, also known as 25. But here's the cool part. The complex part canceled. It went away. The complex conjugate is a number that you can multiply any complex number by to turn it into a real number. So important fact, a plus bi times a plus bi conjugate, ooh, up there, is always equal to a squared plus b squared. It's a real number. In fact, that real number is a squared plus b squared. And let's see, with the time we've got left, I've got 2 minutes. We can make some progress here. Let's use this to do division. And we have, I think, a full plan now. Just how you'd multiply and divide by square root of 2, this time I'll multiply and divide by the complex conjugate of the denominator to simplify the denominator. So, doing that, if you want to compute 1 plus I divided by 3 minus 2i, let's multiply and divide by the complex conjugate of the denominator. 1 plus I divided by 3 minus 2i multiplied by 3 plus 2i divided by 3 plus 2i. This is done by multiplying and dividing by the conjugate of 3 minus 2i, which is 3 plus 2i. Feel good right now? And I guess now if you want to walk it out, you just got to walk it out. There's nothing hard at this point. It's just doing complex multiplication. In fact, without doing anything at all, you already know what the denominator of this fraction is. What should 3 plus 2i times 3 minus 2i be? Oh, well then let's do it. So I know that it'll be a squared plus b squared, but let's FOIL it out. So that'll be 3 times 3 is 9. 3 times 2 is 6 plus 6i minus 6i minus 4i squared. Numerator is 3 plus 2i plus 3i plus 2i squared. Cool. So far, so good. And let's finish this now. What's the denominator simplify to? I think 13. Those cancel. This minus 4i squared is the same thing as plus 4. Because the square is only on the I, not on the 4. I've already squared the 2 to get the 4. 4 plus 9 is 13. So it's all divided by 13. In the numerator, I see 3 plus 2i. So that plus 2i is minus 2. So 3 minus 2 is 1. Plus 2i plus 3i totals up to 5i. Oh, cool. Now I'm just dividing by a real number. You just divide coordinate-wise. 1/13 plus 5/13 I. All right. So, I think I have to stop now because I'm at time. We'll finish up this last few things about complex numbers, why they matter in the context of quadratic equations, and we'll start in on high-degree polynomials next time. Oh, thank you. Oh, appreciate it. Thank you. Yeah. Oh, yeah. Yeah. Yeah, that's yours. I mean, do you want to see the translation between like foiling and the square? Okay, keep going. See you.